Hey all, you hear my voice good? That's awesome. Hey everyone, I am Ahmet and this is my friend Valerio. Today we'll be talking about our ML system we are developing at RAI Institute. And we are really excited to present our hybrid reinforcement learning and imitation learning platform that we are doing robotics using this RAI-based framework. So as an outline of what we are going to be covering today, we'll be going over some background of our RAI Institute, not to be confused with RAI, which stands for Robotics and AI Institute. And we'll be talking about some of the ML research we have been doing. And next, we will be going through some of the different robotic learning approaches, starting from some of the simple ones to the interesting areas we are focusing on. And we will be talking about our training platform solution, where we will be talking about some of the design choices we made there. And later, Valerio will be talking about a particular use case with a brief demo at the end. So let's start with who are we? And we are Robotics and AI Institute. We are aiming to creating these future generations of robots. And we are focusing on longer-term solutions to the most challenging problems. And we are trying to make more robots smarter, more agile, dexterous, and generally easier to use. So the ML infra that we are developing here is to support research at this scale. We are actually creating our system to help our system users to iterate fast on their ideas. So make this platform to actually handle with the messy and DevOps heavy processes easier, to make the users to manage and scale the heterogeneous resources. And also we handle these multimodal static and dynamic data streams within the system that we are developing. So let's actually focus on what is robotic ML from the beginning, a little bit of summary, and what do we actually train. So if you think about robotics ML, it is a sequential decision-making problem. So given the state, we are trying to predict the next actions robot will need to take. So if you take a look at this diagram of a simple robotic decision loop, it starts from the sensors. Robot has lots of different sensors, and it has cameras. So it uses those sensors to perceive the environment and then send those signals to the controller. And the controller is actually a piece of software where in traditional robotics, it was mostly about the model-based systems, policies. And right now, it is more like a neural networks that we are training. And after the controller the policy decide what to act, it sends those signals to the actual robot, like a robot actuators, and then the robot acts. And then in this, our controller, there is different methods that we can train these neural networks. We can use imitation learning or reinforcement learning. So here is a toy demo of diffusion policy on a simulation environment, very simple simulation environment. You see a push-T task, actually. So we have this two-dimensional axis, and then you can see the red plus sign. It's our robot's location, robot arm location. And at each time, the policy predicting 8 next actions, and we see how they are being rolled out, and then the task is to put the T-bar to the color space in this scenario. And using the same principle, we can extend it to the more complicated embodiments. For example, here you can see Boston Dynamics Spot robot is actually doing this robot pick up the bike seat task from different locations. So now let's maybe define what are these imitation learning and reinforcement learning in summary. So starting with the imitation learning, it is basically a learning from demonstrations. So we have a data set that we collected, and we use those in a supervised learning setup, and then we update our policies weights, essentially. And the data that we use is a logged robot demos, which can be collected either from the human experts that are teleoperating the robot, or it could be from the different tools, or it could be coming from the simulations as well. And once we collected those demos, we use data loaders. We can use like array data, we can use torch data sets, different data loaders, and then we feed these trainers with that data in order to do our training. But main popular infrastructural bottleneck within those setups are the data sets, I/O speeds, and regular GPU training loops that, how you use your GPU effectively. On the reinforcement learning side, it is actually learning from the interaction. So you have an agent and you have a simulation environment, which your agent acts inside your simulation environment, and there is like a feedback coming from the environment, and the aim is to optimize that reward. So there is usually no data sets, like a static data sets for certain cases, and the data in this scenario is the online rollout. So we collect the data on policy, and then we send those rollouts to the trainers using replay buffers or RL experience buffers, etc. And the main infrastructural bottleneck here are the simulation throughput, especially if we are doing a vision-based, like if we are using RGB, depth camera, etc. We also need to render the scene. Then it's creating a bottleneck for data collection. And also this same GPU training loops can be extended here. So our question is, well, how do we build such infrastructure that can support these methods and also help us to combine these methods? So it's not that easy, because there are some challenges because how we are actually using simulation and our training infrastructure. So the idea is that we want to experiment different types of training methods, and also we want to utilize Isaac Lab framework, which is NVIDIA's open source GPU accelerated simulation framework. So we want to use them both inside the same experiment that we are running, but the training and the simulation infrastructure are actually different infrastructures. They have different requirements, and it is not always easy to integrate. So if you think about, for example, what training site needs, if you think about their specific runtimes, the model stack using training for serving the model, it might need a certain set of libraries, certain set of versions for the CUDA, etc. And they are best used when they are on the HPC types of cluster, which are like high performance GPU compute like A100, H100, V200s, etc. And the simulations actually runs on the Isaac Lab runtimes, and which is optimized for renderings and rendering and physics for simulation. So, and those devices are specifically requiring RTX type family GPUs, because this is how you should be able to do real-time ray tracing and then do rendering. And you can see, for example, with Isaac Lab, you can scale the environment nicely within a single runtime. And then, in fact, if you try to merge them, put them in the same bucket, same place, there is a very high likelihood that you can get runtime conflicts. And then if you are not able to schedule the correct job on a correct resource, you might get underutilizations, and these whole things can result into slower iteration in your research. So a specific example here, we have different components. Let's say we have device, the CUDA versions, PyTorch build versions, and extra dependencies. And in the sim stack in the middle column, it requires the RTX GPUs, whereas the model stack may benefit from the high performance GPUs. They might have a different CUDA requirements based on what are we using, and for the research it is very fluid usually. The Isaac Lab might have a pinned version, whereas your model might need the latest one, or you can have some of the sim stack might supports some PyTorch builds, but can't others. And there's also extra layers. And think about, for example, if you want to use flash attention in our model, it is very likely that because the flash attention is designed for a certain GPU family, they might not work nicely in this case. In this respect, we did a framework, and our design principle is to make this framework very modular, and we create these different blocks to put on different resources. And then we are decoupling basically this simulation, training, and serving. And then so our users can build their imitation learning or reinforcement learning pipelines easier. And then this gives us like three main features, which is basically you can load data coming from simulation, from on policy as well, both if you are doing some sort of dagger-wise active learning type of imitation learning, and for your RL setups as well. And we can isolate the runtime dependencies for each component inside those blocks, and then allowing them to communicate within the RAI cluster. And then in this way, we can able to schedule the right resource to the for the particular component. So let's dive a little bit in detail one by one, starting with the imitation learning. What is the usual way and how we are basically changing it. So if you are taking a look at the standard data parallel DDP regime, starting from the top, we have policy in our GPU. Each GPU have model replica, and they do this training step. And there's data loader that actually feeds the data to that GPU. And for imitation learning specific, we actually cannot do train data split because of this imitation learning setup. We need to evaluate our policy in an actual simulation environment to see how our training is going. Is it going good or bad? So if we are doing this synchronously, we run training some epochs, and then we wait for the simulation to run. It's not very efficient way of waiting. It's not very efficient. So our solution is to extracting the simulation to the completely different node and then make them run asynchronously and then let the training doesn't stop. And actually, because you extract the simulation, now you can able to use this high performance GPU compute, so your training is much faster. And actually, for certain cases, we are actually doing the model inference inside that GPU in order to do our steps. Some models can be actually larger than our simulation GPU, simulation device GPU memory. So in that case, we can actually extract this model to the larger GPU, and then we can use RAI serve in order to serve and control the rollouts for the simulation. So as a simple benchmark, we simply compared the training where everything is collocated on a single GPU and runs training and evaluation runs synchronously, where we get really low effective a GPU utilization because we have to wait for some certain stuff. And on the training side, when we decouple the training and the simulation and then make it asynchronously, we can get both use a larger GPU and also can have the simulation to run asynchronously, and we can get at least a 1.4 times of speed up. And as you get larger model and more complex simulations, this actually gap becomes larger. So when we think about our framework for the reinforcement learning side, we have also very similar setup. So we do data parallel reinforcement learning on RTX GPUs. And starting from top again, we have the RL policy, and we have this RL experience buffer, replay buffer that feeds the data from simulation. And this time we required to have the simulation over here because it does the data collection. It is where the policy interacts with the environment. But this actually creates this simulation throughput bottleneck because it is hard to render large images. And if you do this small simulations on every GPU, it is a little bit tricky because you need to run your training and then simulation in the same device, and it is not the most optimized thing. So as a solution, we also extract the simulation on a completely different GPU, and then we basically make them communicate with each other. So in this case, you can actually get larger model on a single GPU, and you can get more like a vectorized simulations. Your vectorization can become like a larger when you have the full GPU compared to the training one. So the benchmark we did simply here is we first use only single GPU, and then we collocated everything on the same GPU, and we use the same GPU for doing simulation and doing training. We get our baseline, and distributing them on the DDP approach, we use all of the GPUs for training and sim again. We only get like a 1.9 times speed up because of the data collection is actually like giving us this whole overhead, the bottleneck. So once we decouple the simulation, for example, we take these 2 GPUs to do only simulation and 1 for only training, we get actually beyond, we go beyond 2x speed up. And actually, if you increase more, there is more, this gap is actually reducing more and more. We are also evaluating our asynchronous training update stuff where you can actually completely reduce those data collection bottleneck. So the question is, why this platform and why we are building this now? So because in robotics, there is the research direction towards, there is like a various directions apparently. And one of the most popular one is the building large robotic models for VLAs, which are the vision language action models. And they are a relatively new paradigm, and they are aiming to enabling robots to autonomously perceive, reason, and perform complex tasks in a physical, actual world. So they are actually simple in that sense to LLMs or VLMs, maybe you can say, because they can have a different training stages, like pre-training, post-training, so on and so forth, and where we can actually like handle those stuff, like you can do imitation learning first and then RL fine-tuning, etc. And then that resource direction brings those infrastructural needs we are developing because we need to scale up our simulation within this scale that we are doing this we are going this research direction. And of course, having to be able to scale training is still very important to have to allow more of the matrix multiplication heavy task accordingly. So, and actually, as a last point, we created this system in order that can bring those 2 separate infrastructure in a single environment, in a single system. And we are basically using of RAI because it's very flexible and it works with our very particular case. And now Valerio will be talking about a specific use case, how we do knowledge transfer using this system. Thank you.
Thanks, Amit. So yeah, exactly. So at the Institute, we have these needs in order to be able to hybridize reinforcement learning setups and imitation learning setups. And so on the hardware, as we've seen in diagrams previously in the presentation, it kind of looks like this, where we train some sort of teacher reinforcement learning model, and we'll get into the teacher-student setup in the next slides, to collect some data. Therefore, we kind of dislocate the SIM and the RL policy in different GPUs earlier to get efficiency gains, save all those rollouts to an offline server or otherwise a database, where then we can pick it up in a high-performance compute cluster and run imitation learning policies to try and mimic the teacher's actions in these rollouts. And then finally, in a separate GPU, validate that the imitation learning policy is actually learned successfully, and therefore that this kind of RL-IL setup delivers real gains for the simulation tasks that we needed to. So the actual setup is this. As Amit was saying, a lot of robotics research is kind of increasingly moving in the direction of these very large pre-trained models in the same way that maybe large language models are. And so the way these are actually trained a lot of the time is you kind of create these single task experts, kind of teacher models with RL that are really, really good at doing a very narrowly scoped task. And then you try to take that knowledge and distill it into a student that has to learn from the camera, just like a robot would interact in the real world. And therefore, the kind of game here is to try and get as many of these narrow tasks transferred into the large student, imitation learning trained student as possible. And so the question is exactly this: how do we efficiently transfer the teacher's knowledge into the student such that we can get these very large generalized robot policies? And so at a kind of high level or algorithmic level, this is the basic setup. We have some sort of teacher model connected to a sim. The teacher is an expert at this task, as we said, and takes actions in this environment. These then get saved to an offline server, like you were saying earlier. And so, the teacher takes actions in simulations. Then the student, takes these images from the simulation that the teacher just went through and tries to predict the actions the teacher did. Again, because we assume the teacher is much better at this than the student. This is the best way to kind of compare how well the student and teacher are doing. We then compare these actions, literally as the distance between the teachers and the students' logits, calculate the loss of the student, and update the weights, and kind of so on and so forth. This is also even algorithmically a good setup because it is massively scalable. So because every RL teacher is an expert in one or very few skills, it's actually very beneficial to us to be able to have many of these teachers and sims running in parallel, across different clusters, and all kind of flow into a single student trained with imitation learning that will kind of hopefully come out as a generalist policy that we wanted to. So as for how this maps onto the hardware diagram that I showed you earlier, it's quite simple. Again, we have this beginning teacher step. This is just simply the two GPUs at the beginning, just one sim GPU and one RL policy GPU. We use the RL policy to collect rollouts into the cylinder there, which is kind of expert demos database. And then we take the student and the student loss and offline take the same rollouts, update them through the kind of separate imitation learnings in parallel across many GPUs, reduce them, and then send them to a sim every few iterations or epochs for validation and seeing if the actual policy that we'd like to distill from the reinforcement learning agent has been properly distilled. Great. So to recap, essentially the way that RAI allows us to hybridize reinforcement learning and imitation learning workflows at the RAI Institute is through a variety of features such as RAI clusters with custom compute types, allowing us to distinguish between inference, simulation, and training clusters and kind of orchestrate them all kind of heterogeneous compute types. Dependency isolation by array workers to make sure that each of these kind of heterogeneous workloads has the perfect setup to make it work as efficiently and kind of as smoothly as possible. RAI serve to serve large models that we otherwise could not co-locate with the simulation on a regular GPU, and therefore allowing us to gather data at scale, both in an offline setting, the kind of distillation learning that I just showed, and also in an offline or a joint setting that we kind of are looking to do in the near future, which looks a lot more like this, essentially where we have an RL policy and an imitation learning policy in tandem, kind of doing an online training where the teacher's actions are immediately distilled into the imitation learning student's actions and validated on sim, as opposed to this kind of offline setup that I just showed. Great. And so I'd like to walk you through a little demo of this process through a series of videos. So, the first thing we should do is exactly use these RAI clusters with custom compute types, and therefore start our cluster with 8 training GPUs that, in this case, we'll just say they're A100s. It's some type of high-performance cluster that Amit mentioned, and a few simulation GPUs, in this case, 6000 ADAs, because they allow for ray tracing, which A100s don't, not easily anyway. And so then we can use these to train the teacher policy that we just saw. So what we have to do initially is we just literally submit one command line script to our RAI cluster. The cluster receives it successfully, and therefore in a second now, as soon as the job is kind of set up on the dashboard, we'll be able to skip to the RAI dashboard, which I'm sure everyone here is familiar with, and see that the job is actually running correctly. It's been scheduled. The GPUs are being allocated as we speak. We can enter it, make sure that the duration is fine, and everything starts running. Great. We can then hop over to the cluster and kind of hardware section where we can see the bars on the right. There are these 8 A100s that are all working simultaneously with the 3 ADA 6000 below, making sure therefore that we have this kind of heterogeneous action simultaneously. And then we can hop over to weights and biases and see kind of in real time what the values and losses of the various agents are being trained are. In a second, actually, we'll see as we start to receive the second batch, because it's in batches of 8 steps, and as we receive the second batch, we also start getting actual videos of the simulation from the relevant GPU nodes, and so we can also tell kind of qualitatively how the robot is doing, etc. This is the beginning of training, so as you saw, the simulation wasn't very good. The task here is to pick up a cube, and the robots were barely figuring out where the cube was, but as you can see, if we skip to the end of training, the robots have perfectly learned the task, and therefore we can say that our RL policy has correctly been trained to do the task that we wanted it to do. Great. So now that we have a kind of RL teacher, we have to do the second step of this process in the distillation, which is training the student. So we say we collect some data offline and we store it somewhere, and then what it comes down to is therefore distilling it into the student policy. Follows a very similar setup. In a similar way, we just submit a command line script to our RAI cluster. This is actually the exact same RAI cluster as before, that's the point. And so as soon as this goes through, we will see the exact same RAI dashboard. A second. And also, because imitation learning gets much faster to start up, and so we actually are already getting feedback, kind of losses and gradients back from the cluster in real time, which is also very nice to see. And so we will, there we go. Yeah, same exact RAI job dashboard. It's the same cluster. We're again kind of working with multiple types of GPUs at the same time, and then finally we can, in the same way, hop on over to weights and biases and see at the end of training how the robot's doing. Again, because we're receiving these videos of the training throughout training, we can sort of scrub through the steps here at the bottom of the screen, and we'll see that over time the robot learns how to pick up the cube better and better, faster and faster, and therefore we can say that not only has our RL policy worked, but it has also been correctly distilled into our kind of general student policy as we wanted it to. Great. That's all from us. We'd just like to say that this work could not have been possible without dozens and dozens of people back at home who aren't here presenting in front of us, including a few people in the audience. So all thanks to them. We're also hiring, so if you're interested in this sort of stuff, please do reach out. And yeah, thank you very much for listening. We'll be taking questions for a few minutes.
How well does your teacher-student setup generalize to multiple different tasks? You kind of explained one task with the teacher, one task with the student. If you had, in your example, 10 or 100 different teacher models, how many of those would actually be able to be distilled into the student? And what's the rate of that curve decreasing?
Mm-hmm. Yeah, good question. Do you hear my voice good, right?
Yep,
okay.
We got you.
Yeah, so this is ongoing research, and there's already a similar research that proves that this kind of system works. You can take a look at, there is NVIDIA's work and the others' work on creating these knowledge distillation. We also have some research that is, we just submitted the papers to the conference, but yeah, I mean, it is the system, the technology, mostly we are talking about how we are implementing such systems so it is flexible on RAI.
Makes sense.
But I'm happy to provide some, I don't know, some readings if you would like.
Appreciate it.
Hi. Oh, here we go. Okay. Thanks, guys. A great presentation. The advantage that you have here is since you're, training the student and collecting all that data, the advantage is being able to federate the training later with a lot of other, collections of RL data to train the student. Is that the main advantage? But what I'm saying is that, you're training, if you were going to train the student using RL, you're basically duplicating that when you collect the data, but then you're training the student after that, and I'm thinking I think you alluded to being able to collect data from lots of other examples, and you want to sort of bring those all together into one generalized policy. Is that the main advantage?
Yeah, I think the microphone's not working very well, but I think, yeah, yes, essentially the idea is we can just collect a lot more, like small RL agents are very cheap to run in inference, so we can collect a bunch more data much faster and iterate on kind of, be able to build up a generalist robot policy much more efficiently than we could otherwise. Like if we train these huge models with RL, it would kind of take forever. So this is just a more efficient way of doing that.
Hi, I'm curious about, are these tasks that you're training the general purpose student on, do these tasks kind of like compose, meaning like you break down into like simpler tasks and then compose into a complex task, or is it more of 100 different tasks that the agent student learns but not necessarily like related to each other?
Yeah, I think the task, there's no boundaries of what task you need to like do the distillation. The main like challenging part is from the RL. You need to be able to find out the good reward functions actually. So as long as you have the good reward tasks, good reward functions for any task, you should be able to do state-based RL, and then you can distill that knowledge into the student.
I was going to ask, the environment you showed was pretty, like, had a single cube in a single location. How well does this scale when you're looking at a more noisy environment?
Yeah, you mean multi-node types of scaling?
Just like the environment you're simulating being more complex with more noise and...
Yeah, I think there is two scaling happening here. So Isaac Lab is able to scale a single environment that it is working. So for example, you were seeing multiple robots that are actually doing same thing in the same place. So that's more like a vectorized solution inside the Isaac Lab. You can also scale it to the different RAI actors because our simulation is RAI actor. We can actually scale RAI actors to even to get like a more GPUs to generate, collect data, etc.
In terms of the actual environment too, because I think you were asking about literally the number of objects in the environment, right?
For example, yeah, having like a ton of cubes.
We have work that's currently in the pipeline that shows that it scales fine, like for kind of reasonable numbers of objects.
I think we are kind of over time, but maybe last question.
Okay, yeah, maybe on the training framework, so you basically have shown that by making things asynchronous, by using specialized hardware for each task, you could speed it up. I don't know how much you can comment, but what do you think is the future? Like, what is still missing?
I think we will be very happy if we get more interconnection speed, of course, but that's not always easy things to have, and especially if you are doing training with different types of GPUs, you cannot collocate them inside the same cluster. And then that's why we're actually, the whole research is actually going towards these asynchronous like a training parts as well, which, you know, your training is on policy, but a little bit off, like some steps off policy. So yeah, we are curious about exploring those points as well.
Thank you.
Yeah, thank you all. We are out of time, but thanks for your time. Yeah.
Thanks everyone.